Okay, so this is the second installment of the lecture on attention and consciousness. We will talk about some phenomena that provide insight into the conscious perception of stimuli. So, conscious perception of a stimulus meaning that you are aware of it and you can say that you saw it or heard it or whatever it may be. There are ways that you can get a stimulus to be sensed, so it may still stimulate your photoreceptors and even make it to the brain. In the absence of conscious awareness, so the perception is not there, at least not to the extent that you could talk about it and say that it happened. So these three phenomena are flash suppression, binocular rivalry, and masking. Binocular rivalry has nothing to do with binoculars. This was just a pun. Well, binocular meaning two eyes, and a rivalry between the input from two eyes. In this, when you do a binocular rivalry task, the sensation will remain constant. You'll still have the same photons coming in and stimulating your photoreceptors, but the conscious perception is going to fluctuate between one and the other. All you need to do this is a stimulus like this that has red and blue overlaid on top of each other, and then some of those 3D glasses with a red and a blue lens. Okay, and if you were to look at this image with those kind of glasses, you would see a fluctuation where it'll show blue and then it'll kind of switch to red, switch to blue, switch to red. If you have some of these glasses, I wish we were meeting in person because I have a bunch that I was going to bring. But if you have some, you can look up some binocular rivalry stimuli and observe this for yourself. There are different manipulations that can change the rate at which the stimulus fluctuates from one to the other. And there are also some kinds of stimuli that really kind of dominate and don't really let go, and they'll just kind of stay there and it won't fluctuate to the other one. Faces being a prominent example. If one eye is perceiving a face and the other is perceiving something that's not a face and that's less biologically relevant, the face tends to dominate and be perceived more often. Flash suppression. This is where you have different stimuli presented to each eye. So this is just a little bit different. It's similar to binocular rivalry. One of these, well, there is binocular rivalry going on. It's just done differently than with the goggles. This is described in your textbook, but it's incorrect as far as I understand. What they're talking about is actually motion-induced blindness, which is another interesting phenomenon, but not flash suppression. This video I can post a link to at time 11:15. A researcher goes over what flash suppression entails. This is what it looks like. You have this stimulus presented to the left eye, and then you have some other stimulus presented to the right. And this one presented to one eye is just flashing and high contrast and just dominates your perception. And you can actually kind of try this out on your own. If you stare at this the screen and kind of let your eyes relax a little bit and defocus, if you will, as if you were looking at one of those stereograms, you know, like the hidden, the magic eye pictures. I don't know if you know what I'm talking about, but like those random dots that are all over the place. But if you kind of move your eyes in a weird way and kind of make it blurry and shift them, you'll see a hidden image. If you do that to these two pictures and kind of merge them together, usually it'll kind of fluctuate between one and the other. But if you do that, you'll probably only see that flashing stimulus and not the puppy. Okay, so you're only perceiving that flashing stimulus. However, that image of the puppy is still getting to your brain, even if you're not consciously perceiving it. And so that can still influence your behavior in some way. Masking. So masking involves presenting stimuli on a screen very briefly, like for 29 milliseconds, which is really short. And if you show a white screen and then present the word and then show a white screen again, you'll typically be able to consciously perceive it. You can say, oh yeah, I saw the word grove. However, if you precede it and follow it with these masking patterns, kind of this random jumble of lines or something similar to this, if that's shown right before and right after, it's almost never perceived. So somebody would, if they're shown this, they would say, I didn't see anything. Okay. However, that word is still getting into your brain, even if you're not consciously perceiving it. What does brain activity look like if you are seeing a word and you're consciously perceiving it such that you can report that versus not? It's, you kind of have this widespread activity, kind of this ignition pattern it's kind of referred to as, where if you have these masked words, you'll see a little bit of activity. So something is happening. You can see some visual cortex or some occipital lobe activity here. For masked words, if it's a visible word, though, it's widespread all over. So you have this ignition of brain activity. Okay, so this can be, this kind of gets at what your brain might be doing, and what regions of the brain are maybe involved in consciously perceiving a stimulus, even if the sensation between these two conditions is the same. So EEG, I want to introduce that briefly just because it's used in consciousness research, and there's a, in your textbook it talks about a binocular rivalry study that uses EEG. As we mentioned before, this measures electrical activity from cells under the scalp. Sometimes this is done, measurements are done continuously, so just seeing fluctuations in brain activity over the course of, a night, if you're studying sleep, for example, or over the course of a day, as if you're monitoring for epilepsy, monitoring for an epileptic seizure, for example, and just seeing how brain activity goes up and down, how it oscillates. Sometimes this is used to measure an evoked potential, so how brain activity changes on a short time scale in response to some stimulus, like if you're presenting images on a screen and you want to see how brain activity changes in response to faces versus houses, for example. Okay, an advantage of EEG, and these are concepts that also connect to the advantages and disadvantages of fMRI. An advantage is that it gives a good measure of cortical activity in real time. Okay, so this is has very good temporal resolution. It's telling you how brain activity is fluctuating on a very short time scale, on the order of milliseconds. Okay, so you can see how brain activity goes up and down. fMRI, on the other hand, has this lag due to blood flow. Okay, so you can have, brain activity that's going up and down, but then all you're going to see is just kind of this general up, as and not even at the same time, but delayed by a few seconds. And you can infer, oh, there was some kind of activity that happened there, but it doesn't have very good resolution with respect to the time, the temporal resolution. A disadvantage, though, is that it's hard to localize where brain activity is happening. So EEG has pretty poor spatial resolution. You can kind of get a feel for, oh, there's some activity in this lobe, or towards the back or towards the front. There are actually some mathematical problems with being able to localize it for sure, even to that extent. But you can get some degree of localization, but nowhere near what you can get with fMRI when you're on a millimeter scale, seeing where brain activity is happening. And you also can't get deep. EEG pretty much only tells you what's happening on the cortex. If you want more details on EEG, you can refer to Chapter 3. All right, and that is the end.